did trig substitution. Hopefully that homework went pretty good. We might have some time to go over questions at the end, but we're going to look at a new technique today called partial fractions. So we're going to spend today and tomorrow on this, look at how we integrate rational functions by this method we call partial fractions. So kind of switching gears a little bit. You shouldn't have to use too many trig functions in this one if you're tired of those. So we're going to go back and work with some rational functions instead. So let me give you a little bit of background on this. Our goal is to take a rational function and express it as a sum of simpler fractions, which we call partial fractions, that we actually know how to integrate. Now, does everyone know what a rational function is? What gives that away? Anyone know? Rational function? Nope, yeah, Nathan? Yeah, that's like a rational number. That's true. A rational number is something that doesn't repeat, or irrational number repeats, rational number either is a repeating or terminating decimal. Irrational numbers don't. They're numbers like pi and e. But a function, what makes it rational is actually just that it's in fraction form. So that's kind of what it is. So it will look like this. Your function is basically a fraction of two polynomials. So we call them p of x and q of x. And we got to make sure here q of x, of course, doesn't equal 0. But that's really the form it is. It's two polynomials being divided. So that's what a rational function is. Does anyone know what the graphs would look like of these? Like if you had x over x plus 1, anything like that? Anyone know what those would look like, the graphs of? Yeah, there's like little pieces to it. The main one, you don't need to write this down, but kind of the simplest rational function is 1 over x. And it has like these little pieces like this. Have you seen that before? 1 over x looks like that. So rational functions tend to have asymptotes because they have places where it's undefined, like here it's 0. So they may have asymptotes and they can have more than 1. And then the graphs kind of fit in between all those asymptotes. So that's just a little bit of background on rational functions, so you know a little bit about what they look like. So that's the kind of thing we're going to be working on integrating. Now, in order to do that, we kind of reverse the process of getting a common denominator in order to put it into a form that we can integrate. Because I'll show you why. If you try to integrate, let's say 5x minus 3 over x plus 1, x minus 3, let's look at it in this form. This is a bit hard to integrate. Okay, so if I'm like, oh, well, how would I start this? Well, I could distribute out the bottom and try a u substitution, but it would still be difficult to do. If you distribute the bottom, you get something like x squared minus 2x minus 3. And so a u substitution might be, well, I might let u be this x squared minus 2x minus 3, the denominator, but then the derivative is 2x minus 2, and that will be difficult to get it to match up to the numerator. The numerator here is 5x minus 3. How do I make that look like 2x minus 2? There's no real easy way to do that. So substitution is difficult here. So in this form or even this form, it's hard to integrate. So what we want to do is kind of reverse this process I'm going to show you. Now what we're used to seeing is getting a common denominator. Well, in algebra maybe. I don't know how much you did this in Calc 1, but definitely did this a lot in college algebra. So let me show you this. So in the past, when we have had something like 2 over x plus 1 plus 3 over x minus 3, they've asked you to simplify this, right? And that usually required you to get a common denominator and put it together. So let's see if you remember how to do that. How do we get a common denominator here? What is our common denominator? Yeah, both of these, right? So our common denominator would be made of both of these, what we call linear factors. So we would rewrite them each with a common denominator. In order to do that, let's say for the 2, what would I do to adjust the 2 here? Would have to, yeah, the part that's missing, right? So I'd multiply this by x minus 3 and this by x minus 3, and you get 2x minus 6. This one you'd have to multiply by x plus 1, and you get 3x plus 3, right? So you multiply by the factor that's missing, and then you can combine that to make one fraction, right? So when I combine the numerators, what do I get on the top here? 5x minus 3 over x plus 1 over x minus 3. So notice I got this result. So this part you are really used to doing. I see this, I get a common denominator, I simplify it, and I get one fraction. But this form is difficult to integrate. However, if I integrated this form, would that be a little bit easier? So let's check on that a minute. So what if I asked you instead to integrate the 2 over x plus 1 plus 3 over x minus 3? Could you integrate that? Could I integrate this piece by itself, 2 over x plus 1? Sure. What would you integrate it to? It would be some sort of natural log, right? Natural log of x plus 1. In fact, it would be 2 natural log of x plus 1, right? And this would also be a natural log, a 3 natural log of x minus 3. So this form is much easier for us to integrate, but most of them start out like this. So what we're going to be doing today is basically working backwards. We're going to go from here to here. Okay, so where I have 2 fractions instead of one simplified fraction. We want to go this direction. So that's a process called partial fractions. Let's make a note here. This is called partial fractions when we work backwards like this. I want to take something like this and split it up into what we call 2 partial fractions, because this is much easier to integrate in this form. Okay, so that's kind of the reasoning behind it. When I start with something like this, it's like, I don't know how to integrate that. So I want to work backwards and say, well, what 2 fractions did it come from? And put it into that form so I can actually integrate it. And that's called partial fraction decomposition, or making partial fractions. Sometimes we call it decomposition. It's like breaking it down. That's what decomposition means. Think of decomposing things in the earth. That's what usually happens there. So that's what we're going to do here. So I'll make a note here. This is hard to integrate. This one down here, much easier to integrate. So that's the process. Now, how are we going to get there? That's the part I'm going to show you today. So how do we get to this form here? Okay, so a couple things. We're going to be working with these rational functions. Like I said, they're kind of in this form of polynomials divided by another polynomial. And we're going to try to make it into a simple form that we can actually integrate. So I'll show you that. But the first thing I want to make a note of, if it's what we call improper, the first thing you should actually do before you try to break it down into partial fractions is to actually divide it using long division. Do you know what I mean by improper? How is a rational function improper like that? You know what an improper fraction is? Yeah, that would be improper as well. But for fractions, what's an improper fraction you're used to seeing? Like 10/7, right? Where the top is bigger than the bottom. So in polynomials, it'd be if the top has a bigger degree than the bottom. So this is when the numerator has a larger degree than the denominator. So I'll write that here. So when the numerator has a larger degree than the denominator, it is what we call improper. And if that's the case, then actually the first step you always want to do is divide using long division. So it basically will become this. So if you have this rational function, where is improper, you can divide it out and you'll get some polynomial, I'll call it s of x, plus some remainder that you can rewrite as a fraction. So you'll want to divide it to get some sort of polynomial, and then the remainder you'll rewrite in fraction form, and that may be something you could integrate, or maybe you'd have to break it down, but you would want to put it into that form. Okay, so that's the first step. Always check if it's improper. If it is, start with that. So let me show you one like that. In this one we've got, it's the first one here with a rational function, the integral of x to the 4th over x minus 1. Okay. Now, some people here are tempted to split this up into two fractions. Can you do that on this one? No, right? Can you ever split up a denominator? No. A numerator you can split up over the denominator, but a denominator you can never split. So just be careful about that. Is this an improper fraction that we have here? Yeah, because what's the degree on the bottom? 1. So this is a 4 over 1, so it's improper. So what you can do first is long division. You thought you left that behind, but no, long division with polynomials coming back to haunt us. Okay, so by long division, I mean do the long division. You take x minus 1 into x to the 4th. Yeah, do you remember how? Okay, so what do you multiply x by to get x to the 4th? X to the 3rd. You put that on the top. And then remember, you're going to distribute and put this underneath. So by distribute, I mean times it by the x. That gives you x to the 4th, which is what you want to have happen. But you also need to times it by what? The negative 1. So you get negative x cubed. What do you do with these terms in long division? You always subtract. And you subtract the whole thing. So you got to be careful because your signs are going to change. Now, technically, how many x cubed are up here that you need to subtract from? 0. So you could put, some people like to put zeros in there for those missing terms, if that helps you keep track of them. And that's kind of why I indent one, because it's going to have 2 terms, so that's why I kind of put it over the second term there. So these, what happens to the x to the 4th? They cancel, right? 1 minus 1, there's 0. How many x cubed are you going to have? 0 minus a negative becomes a plus, so that gives you 1x cubed, right? So you can distribute that through. Sometimes I'll show the distribution and circle the new sign. That becomes a plus. Okay, what do I multiply x by to get x cubed? X squared, a positive, right? So we call it plus x squared. And you distribute on the outside again. So that will give you x cubed minus an x squared. And again, you subtract. And up here, remember, the term is really 0x squared. You can drop that down. Okay, if you subtract here, the x cubes should cancel. That's how you've set it up, right? That gives you 0. Here, this makes a plus. And you get 1x squared. And you just keep going, right? There's long division. What do I multiply x by to get x squared? X, right? So plus 1, x. That's an x there. So that gives you x squared minus x. Keep going, subtract. Drop down the 0x if you want. This also becomes a plus. So you get 1x. What do you multiply x by to get x? 1. So plus 1. That will give you x minus 1. You distribute the negative through. And what are we left with? 1. What do we call 1? The remainder, right? It's the remainder. But to write it in fraction form, what do you write it as? 1 over the x minus 1. Yep. So the fraction is 1 over whatever the divisor was. Okay, so now we've rewritten it in this form. There's this polynomial piece plus the fraction remainder. You'll still have kind of this remainder piece. So then the question is, once I've divided, now I can rewrite this in this form. Can I integrate this? I hope so. But we'll see. Oops, that's a minus, sorry. Okay, so I rewrite it in this form, and then I ask myself, can I now integrate it? I think so. These will be easy, right? Can I integrate 1 over x minus 1? I think so, just a natural log, right? So then we can integrate each of these. So this becomes 1/4 x to the 4th, right? 1/3 x to the 3rd. What else? 1/2 x squared plus x. Right? The 1 comes from x. And then this should just be the natural log of x minus 1. Now, here's again another quick way to integrate here. These will always become natural log as long as this derivative of the inside here, if you let this be your u, if the derivative is 1, you don't need to worry about adjusting that at all. You can just make it the natural log of whatever's in there. If there's a derivative here of a constant like 2, you may have to divide by that when you do the natural log. Okay, so that is always your first step if it's improper, is to do that division. Now, sometimes in the division, you'll get a fairly complicated expression for the remainder here. Then you may have to also use some partial fractions, which is the piece I'm going to show you here. But always start with that step if it's improper, and that's the first thing you want to check is, can I just do long division? Maybe that will be all I need to do, and then I can integrate. So if that's not the only thing that you need to do though, what if you're stuck with something you don't know how to integrate? I'm going to show you a couple cases of how to do those. So how do I do this partial fraction decomposition if I need to do that? So we're going to look at a couple cases. It does depend on what the factors of the denominator are made up of. So case 1 is when your denominator is the product of distinct linear factors. Now distinct means unique. So they're all unique. There's none that are the same. So here means they would all be different linear factors. You know what linear means? What does a linear factor have to have in it? Yeah, x to the which power? Makes the first power, right? If you had an x squared, that's called quadratic. So you want to make sure when it's linear that you only have x in the factors. It can't have x squared in it. So they are unique and they only have x as their highest power, x to the first. So it can't have any repeated factors in the denominator. So if that's the case, then there will exist constants that you can decompose it into what we call partial fractions. So we can take this polynomial, I'll call it p of x over q of x, and we will be able to find constants. And we're going to usually call them capital letters. So we can find these constants like a for the first linear factor, ax plus b. And then plus b for the next linear factor, for cx plus d, and so on. So all of these will be unique linear factors where they only have an x to the first power and they may have constants with it, and so on. So there will exist all of these constants that I can find and break these down into simpler fractions. Okay, so I need to go find them though. What are the constants? A, B, C, and so on. But all those linear factors will have their own constant in the numerator. And then my goal will be to find out what those are. Okay, so there will exist these constants A, B, C such that I can rewrite it in this form. So I'm going to show you what I mean by that in the next one here. So let's look at that one. So this one is the integral of x cubed minus 4x plus 1 over x squared minus 3x plus 2. Okay, so that's an x cubed minus 4x plus 1 and x squared minus 3x plus 2 is on the bottom. Okay, so remember, first thing you're going to do anytime you approach a problem in this section, ask yourself, is it improper? Is it improper? Yes. What are the degree? It's 3 over 2, right? So when this is bigger, it's what we call improper. So what's the first thing I need to do before I start anything else? What did I say when we have to do when it's improper? Long division. So I got to do it again. Okay, so that's the first step anytime it's improper. Okay, so that's the first thing you'll do here. Notice what's missing in the top here. What term is missing? The squared. So you might want to insert the 0x squared if you like those all to line up. Sometimes that's helpful to do. Okay, so long division, always do that first if it's improper. Okay, so if that's the case, let's see how we're going to divide this. So let me start with Benham. What do I multiply x squared by to get x cubed? X. So you only need x. This one has 3 terms, so I'm going to indent 3 terms. I'll put my x there. It's distributed times all of these, right? So Angie, what am I going to have if I distribute these? Yep. Yep, minus 3x squared plus 2x. Good. So that goes underneath, and then you're going to subtract all your terms. So this becomes a minus x cubed and those cancel. This should become a, so this is plus, this one will be minus, that will become a plus. So you get positive 3. This one will become a minus, so you get negative 6x. So I'm just going to circle the new signs once I distribute them in. Okay? Alright, Joel, what am I going to multiply x squared by so it matches up to 3x squared? Positive 3, right? So a plus 3. We distribute that through. Natalie, what am I going to get underneath here if I distribute the 3? Yep. Minus, close, 3 times 3, 9x. There you go. And then, there you go. Yep, good. Yep, you're right. It did show up at the end. Good. Alright, good. So now, again, we subtract all of these. Let's see what we have left. This is a minus, a plus, and a minus. So these are 0. This one is a 3x, right? And a minus 5. Does that look right? 3x minus 5. Okay. Can I keep going in long division? Can I make x squared look like x? No. Now I'm done, right? So this is my remainder. So it's a 3x minus 5. What does it go over? Yes, got it. The divisor, x squared minus 3x plus 2. Okay, so now I have this integral. It is the integral of x plus 3 plus 3x minus 5 over x squared minus 3x plus 2 dx. Okay. Now I ask myself if I can integrate this. So can I integrate x? Sure. 3, no problem. Can I integrate this fraction? It looks hard, right? And the reason is you can maybe think about the only way we could do it at this point is possibly a u substitution. Like if we let u be the denominator, the derivative is 2x minus 3 though. Is that going to match up to 3x minus 5? That's going to be hard. In fact, impossible. So this is one where we want to do the partial fractions. We want to decompose it into 2 smaller fractions that I could integrate. So here's how we're going to figure out how to do that. I'll show you the process. So take what you want to decompose. So the 3x minus 5 over x squared minus 3x plus 2. You don't need to worry about the first part of it at all. Now you're just working with the fraction part. And what you want to do is make sure you get the denominator factored. So what does the denominator factor into? Let's see, it looks like what? X, yeah, Taylor's got it there. So x minus 2 and an x minus 1, right? Because that multiplies to positive 2 and adds to negative 3, so you get it factored. Now, we look at these and say, are these linear factors? What do you think? Are those linear? Yeah, because they have x to the first. So they are linear and they're distinct. They're not the same factors. So we can break this down by doing the following. So we take a fraction for each of the linear factors. So the x minus 2 and the x minus 1. It will each of those linear factors will have its own fraction. And our goal is to find the constants that belong on the top. So I'm going to call them A and B for now. Okay, so my goal is to figure out what constants do I put on top so when I add these together it simplifies to this. Okay, so I've got to figure those out. This now, how do I figure that out, becomes an algebra problem. Okay, so let's go ahead and do a bit of algebra here. So the first thing I will do to figure this out is kind of clear out the fractions. So let's see if you remember how to clear fractions in an equation. So here's the equation I'm solving. Okay, this equal to that. I'm going to try to solve for A and B. So if I clear out fractions, how do I do that here? What would I multiply by? How do I clear these fractions out? Anyone remember if you were solving? You wanted to both of them, right? Yeah, the whole thing, right? So I basically need to take all of this, the entire equation, and multiply it by x minus 2 and x minus 1, right? Multiply by the common denominator. And that will apply to all the pieces on the left and the right-hand side. Here's the algebra. Okay, what's going to happen to this left fraction? What will be left? 3x minus 5, right? The bottom 2 cancel. What will be left on this fraction with the a? Yeah, x minus 2 cancels and you'll have x minus 1. What will be left with b? X minus 2, because x minus 1 cancels, right? Okay. So clear the fractions. So multiply by a common denominator, they will cancel all the denominators. Okay, now we're going to solve for a and b. Now, here's the easiest way to do it as we begin, and it usually will work here if you have linear factors. It's not usually a difficult way to do it. What I'm going to do is plug in some values for x that make these factors 0. That way I can get rid of 1, and hopefully I can then solve for the other constant that's left. So what number would I put in here to make this 0? Okay, so go ahead and plug in the entire thing, x equals 1. Okay, if I do that, what do I get on the left? If x equals 1, this 3x minus 5 becomes negative 2. This whole thing becomes what? 1 minus 1 is 0, right? That's gone. So the a term is gone because I put in 1 and that makes the whole thing 0. Okay. What am I going to have times b? b times 1 minus 2 is negative 1. And now could I solve for b? How do I get b by itself? b is 2. Divide by negative 1, right? And b is 2. Okay, so I've got one of the constants already. So I know that 2 is going to be the numerator of this fraction with the x minus 1. Okay, what other x would I want to plug in here? 2. Okay, so 1 makes this 0. Let's try the other one. Now x is 2. Okay, so what do I get on the left? 3 times 2 minus 5 is 6 minus 5 is 1, right? And then you would have a times, what's 2 minus 1? 1. What happens to this b term? If x is 2, this becomes 0, right? So that b term is gone. So it'd be b times 0, and that's gone. So what is a now? A is 1. Divide by 1, you get a is 1. So I found both constants. And so now I know that this breaks down into 1 over x minus 2 plus 2 over x minus 1. So now I can take this piece and break it down into 2 fractions that I can integrate. So what will that look like? So let's rewrite our integral here. So don't forget, you still have the x plus 3 in the front here. Okay, so there's x plus 3. That's still there. This fraction now I replace with these 2 terms with the 1 and the 2 and for a and b. So this one had a 1 over it, so it's 1 over x minus 2. The b, right, was 2. So this becomes 2 over x minus 1. Okay. So I've broken this fraction down into 2 simpler fractions that hopefully I can integrate. Okay. So once you found a and b, that's the partial fraction piece. So then I rewrite them as my 2 fractions in the integral, and then I try to integrate. Hopefully I can from this point. So that's how you do it. You want to set it up with 2 constants over each linear factor. Use some algebra to figure out what those are, and then replace those into the integral. So let's see if we can finish this off now. Okay, so let's integrate the x plus 3. Start with that. Riley, what am I going to get if I integrate x? Good. And what about for the 3? 3x. Okay, good so far. Now both of these will basically just be natural logs. When you have a linear factor on the bottom here, these become just natural logs. They're like u to the negative 1. So this one will just be a natural log of x minus 2 absolute values. Don't forget those. I will check inside. What's the derivative of the inside here? What's the derivative of x minus 2? 1, right? So anytime there's a derivative that's a constant, you would divide by that, but when it's just 1, you don't need to worry about. Now, when there's a 2 out front, or 2 in the numerator, that just becomes a constant you pull out front. Because remember, you could write that as 2 times 1 over x minus 1. So the 2 is just a constant, and then you still get the natural log of x minus 1. Okay, so this is a quick way to do those. Technically, you can do a u substitution for x minus 1, but that's kind of a long way to go. And again, check the derivative of the inside. As long as it's 1, you don't need to worry about anything else. And you put on the plus c. So any numerators that are constants, those are just can be pulled in front of the natural logs when you integrate those, and then you're done. Okay. So partial fractions usually are required if you see a fraction like this that you don't know how to integrate. So especially if the bottom is something with an x squared, that's going to be something you might look for linear factors of and try to do what we call partial fractions. So questions on that one? That's kind of the main idea. Okay, let's try another one here. So what's the very first thing we always check for? Improper. So let's start that in this one. Is this an improper fraction? Austin, what do you think? It's 4y squared minus 7y over 12, and then y cubed minus y squared minus 6y. No, this one isn't, right? Because it's 2 over 3. So the top is not larger than the bottom degree. So I do not need to do long division on this one. Maybe you're saying, thank goodness, because you were tired of that. Okay. Yeah. So, yeah, when the top is smaller than the bottom degree, then you don't need to do long division. Okay? Oh, yeah, sure. 4y squared minus 7y minus 12. And then on the bottom, it's y cubed minus y squared minus 6y. And there are limits on this one from 1 to 2. Okay, so I can't do long division, but obviously this looks fairly complicated to integrate. So here's what I'm going to do instead. If I can't do long division, I'm going to see if I can break this down into simpler fractions. So in order to do that, I'm going to go ahead and factor its denominator to see if I have those linear factors. Okay? So let's look at that. If you have y cubed minus y squared minus 6y, could I factor that at all? What could I factor out of there? First a y. So I'm just going to write this on the top so you can see it here. So I could first take out a y out of everything, and then I'd have y squared minus y minus 6 left. Can I factor any farther? Maybe. What do you think? Sometimes quadratics we can factor, right? Could I factor this one? What multiplies to negative 6 and adds to negative 1? Negative 3 and positive 2? Yeah, that should work. So I can take the numerator or denominator and I can factor into these 3 factors. I'm going to go back to factoring if you remember how to do that. Are these all linear factors? Yeah, because they're all to the which power? To the first, right? Y to the first, y to the first, y to the first. There are 3 distinct linear factors here. Y minus 3, and y plus 2. Those are all linear. They're all different. Okay, so this I'm going to factor into y minus 3, y plus 2. If I have distinct linear factors, then I should be able to break it down, do partial fractions for each one of those linear factors. So let's set that up and solve. Okay. So this time I have 3 factors in the denominator. Oops, I don't need a dy. So I'm going to set up 3 different fractions. So I need to find the constant that goes over the first factor, which is y. And then a constant that would go over the second factor, y minus 3. And the third one, y plus 2. So there should be constants for each of those fractions that go over the linear factor. Okay, now we just got to go find them if we can. So hopefully can. This is where the algebra kicks in. Alright, now let's go ahead. What's the first step we do? Remember from the last example. Once I've set up my equation, I know how many constants I'm looking for. Multiply by the common denominator. Exactly. What is it here? It's basically all 3 of them, right? So you're going to multiply by y minus 3, and y plus 2. Clear out the fractions. Then we have an equation hopefully we can solve. So on the left, you always should clear the whole denominator out and just be left with the numerator. So 4y squared minus 7y minus 12. Okay, so the question is then what's left with the a? what will be left with the a? The y's cancel, right? So it has how many factors with it now? 2. Y minus 3 and a y plus 2. Right? So the y canceled out, but when I distribute it to there, I'll still have y minus 3 and y plus 2. Okay, Taft, what am I going to have with the b? What factors will be with b? Yeah, because y minus 3 cancels, so then you have a y and a y plus 2 with the b. And just about, what about with c? Yep, so y plus 2 cancels, so these two are left with c. Okay, so that's the first step, clear out the fractions. Next step, what should we do next? Sure, that would be one option, right? Now we plug in different y's to try to get some of them to zero out our factors. So Austin said y equals 3 first, so let's do that one first. So you plug y equals 3 into this entire thing. So the left-hand side, got to figure out what that is. Let's see. So 3 squared is 9 times 4 is 36, right? Minus 7 times 3 is 21. I'm going to just type this in so I don't forget that. So 36 minus 21 minus 12. I'm getting 3. Okay. What's going to happen to this a term? Yeah, it zeroes out, right? 3 minus 3 makes this entire term 0. Okay, what about the b term? Will that go away? No, that one won't. So it'll be b times, what is it? 3 times 3 plus 2 is 5. 3 times 5 is 15. What about the c term? Gone. Perfect. Because now I can solve for b. So if I get the other two terms to cancel, I've got b left. What do I get for b? Yeah, 1/5. Okay? So yeah, so you'll have a fraction, but that's okay. Okay, so let's look at the next one here. So what else should we plug in besides 3? 2, negative 2, right? Negative 2 will be good because that will zero out this factor here. So, okay, let's get this one right. On the left, let's see. So negative 2 squared is 4. 4 times 4 is 16. Negative 2 times negative 7 will be plus 14 minus 12. I'm getting 18 on that one. That sound right? Good. So, which terms zero out? A term, right? And what other one? B term. So now we just have C times negative 2 and negative 5. Is that 10? Yeah. So C times 10, divide both sides by 10. What is C equal to? Looks like 9/5. Okay. So that's a fraction 9/5. All right. Let's see. McKelty, what do you think our last y should be? 0. Okay, so for just the y term, you want to use 0. So let's make y equals 0. I like that one because this is easy. 0, 0, negative 12 is what we get on the left. B and C terms should now zero out because they have it times y. Those are zeros, so those are all 0. So we just have the A term left. 0 minus 2 is negative 3 times 2 is negative 6. So what is A? A is 2, it looks like, right? Okay, so you can get fractions, that's fine. But we found all our constants. So now I take this integral and I rewrite it as these three fractions with A, B, and C plugged in. So I'm going to rewrite that now with those three terms. And then I'm going to hopefully be able to integrate. We'll see. Okay. All right, so now I have the integral from 1 to 2. Let's see. A, I'll just start with the first term. A was 2, so it's the term 2 over y. So that was 2 over y. B was 1/5. So I'm going to write it as 1/5 over y minus 3. And then C was 9/5. So that goes over there. Y plus 2. And I like to leave them as fractions on the top. Some people like to put the 5 down in the denominator, but really for integration, it's just helpful if you know that constant kind of off by itself in the numerator. So you don't necessarily need to like move this 5 down to the denominator or anything. It's actually easier in this form to integrate. So, or pulled out in front of the fraction, that would be okay too. So, okay, so let's integrate this and see what we get left here. So when I integrate each of these, notice these numbers on top are just constants, so technically here I just have a 1 over y. So the constant comes out front too, and it just becomes natural log of the denominator y. Okay. Same thing with this one, 1/5 natural log of the absolute value of y minus 3, and then a 9/5 natural log of the absolute value of y plus 2. Okay, so that's why I kind of leave those in the numerator or even pulled out front. Those constants just go in front when you integrate the natural logs. Okay, now this one I don't put on plus 0. I've got limits 1 and 2. So I just plug those in, simplify, and you're good to go. Okay, let's see if we can do it here. So tell me what we get. Now the good thing is, I don't know if we'll need, well, maybe we'll need some absolute values. So this is 2 natural log of 2. So since 2 is positive, I can drop off the absolute values. Plus 1/5 natural log. Now here you get 2 minus 3, right? Which is technically what? -1. So the absolute value of that will be 1. So that's where absolute values are important. That becomes 1. Plus 9/5 natural log of 2 plus 2, which is 4. Minus 2 natural log of 1. Plus 1/5 natural log of 1 minus 3 is -2, so that becomes a 2 when you use the absolute values. And 9/5 natural log of 3. Now, there are going to be a lot of natural log problems. One thing you know you can get rid of is any natural log of what? 1. What's natural log of 1? Always 0. So those are nice. Those go away. And then you might just see here if there's some like terms that you can maybe combine. Let's see. Anything we could combine on this one? Yeah, the natural logs of 2, right, are the same. So you could do 2 minus 1/5. So 2 minus a fifth, that's 10/5 minus 1/5, 9/5, right? So 9/5 natural log of 2 would combine these two. And then you'd have a 9/5 natural log of 4 minus 9/5 natural log of 3. And there's probably some more like simplifying you could do here. Maybe you could combine the 9/5, pull that out, factor it out. And actually, natural log of 2 and natural log of 4 you could make similar, couldn't you? Do you know how? Okay, what do you got to do? Right. Remember, 4 is 2 squared. And in natural logs, whenever you have a power, you could actually drop that down in front and make that a constant in front. And then they would actually be the same. So you'd have 9/5 natural log of 2 plus 18/5 natural log of 2, and then you could combine those. And then those can be combined, and what does that give you? 27, I think? 27/5 ln of 2 minus 9/5 ln of 3. So that would probably be the simplest form, and like I said, you could also maybe factor out a 1/5, but there's some other forms. As long as you've done at least simplifying like terms here, that's what I'll be looking for. If you can simplify all the natural log of 2s and 3s, that will be good. So, okay, so that's partial fractions. I think that's as far as we're going to go today. We're just going to look at case 1. So as you get to your homework, a couple things to remind yourselves to do. Number 1, check for an improper fraction and make sure you divide by long division if it is. Then when you get to whatever's left, if you can factor into these distinct linear factors to make sure you break it down into those partial fractions and find the constants so you can rewrite it and hopefully then integrate it. And a lot of times they'll integrate into natural logs. So I think that's it. So the first part of the assignment, they should just be kind of all of these, either where you can divide, because they're improper fractions, and then they should be also case 1 where you could separate them into distinct linear factors. And tomorrow we'll look at some other cases where they might be repeated or they might have quadratic factors. So we'll look at those, but that's what we'll start with today at least. All right, let's see what else. Let me go over any homework questions. I might have time for a couple here, and I'll send the attendance around too before I forget. Okay, homework questions, anything from 7 that I need. 7.3 part 2 is what we're on, right? Yes, any problems on those? Yeah, Nathan? 12, okay. So if you want to stick around for 12, you can. So this is the integral from 0 to 2 dt over square root of 4 plus t squared. Okay, that's the one, right? Nathan, does that look right? Okay, so we got to do a trig substitution. What'd you let t be in this one? 2 tangent theta would be the best option here. Yeah, definitely in the one where you want tangent. So then dt, the derivative of that is 2 secant squared. The derivative of tangent is secant squared of theta d theta. Make sure you're still putting on your domain restrictions here. For tangent, it's between negative pi over 2 and pi over 2. And this one had limits, so I don't know, did you change the limits, Nathan? I probably would. Yeah, you might want to because they do turn out nice. So I didn't go back to t values, I just used theta. So like when t was 0, I'm not saying you had to, it just makes it a little easier. So if you set t equal to 0 and divide by 2, you basically have to see where the tangent of theta equals 0, and theta would be 0 there. And then when t equals 2, you can divide both sides by 2 and you get tangent of theta equals 1. So that's at pi over 4. So you could change the limits on this one to pi over 4 and 0. And that makes it a little bit easier. So let me go ahead and replace dt with 2 secant squared theta d theta. It's in the numerator. In the denominator, you'd have the square root of 4 plus 4 tangent squared. Does that look familiar so far? So what comes out of here is probably a 2 secant theta. Is that what we got in the denominator? Okay. And then the 2's cancel and one of the secants cancels. So you basically just have secant of theta. Good so far? Just secant, right? So the integral of secant is the natural log of secant theta plus tangent theta. And then because I changed my limits, then I just plug in pi over 4 and 0. But you maybe did you go back to t? Or no? Yeah, you might have. But I think this is actually a little bit easier. So if you change your limits, it might make it a little bit easier here. Because then you can just find the secant of pi over 4 and the tangent instead of going back through the triangle. And then also secant of 0 and tangent of 0. So let's see if I remember what each of these are. Let's see. So the secant at pi over 4, the cosine there is really square root 2 over 2. So if you flip it over, that becomes just square root of 2. It's like if you simplify it. What's the tangent at pi over 4? That is 1. What's the secant at 0? Same place, cosine is 0, which is at 1. And tangent of 0 is 0. So you basically get the natural log of the square root of 2 plus 1 minus the natural log of 1, which is 0. Yep. So I think that's it there. Natural log of the square root of 2 plus 1. And I can drop the absolute values because it is positive inside. So I don't need to worry about the absolute values on there. Does that one make sense now? Yeah. No, you might not change limits. Any other one? Yeah, Riley? Is that the one? Okay. Oh yeah. So main thing is probably did you set it up right correctly? So let's see. That's the volume one, right? Was it volume? Mm-hmm. So this one, when it's going around the x-axis, the main way to get the volume here is like you integrate the area of the circle that it would make going around, which is pi r squared. So that's kind of actually how you would sort of set it up here. So in 37, what is it? It's 9 over x squared plus 9. Is that the function? Yeah, and then you have y equals 0, x equals... yeah, sometimes they'll do that because they gotta go. Well, I'll finish. It will be in the recording. Okay, so on this one, I don't know, did you sketch it at all? I think it had, what did it look like? It started at 3, if I remember right. I'll draw a little sketch for you so you see what I'm talking about here. The radius is really just its function. I think I sketched it here. Yeah. This one, it goes, I think it's something like, I don't know, what is that at 0? At 0, it's 1, right? So it goes from here, kind of goes out like this, and then it rotates around. So it's kind of rotating like this. That's its picture. And this is the equation. So when we look at these circles, the radius here is just the function value. So when I set up my volume on this one, I use the x values. This is going from 0 to 3. So I'm going to integrate from 0 to 3, basically the area of a circle. So pi, and then this is the radius. It's 9 over x squared plus 9 squared dx. So that becomes your radius. So you set it up right? No, yes. Wait, have you guys gotten to this in Calc 1? No volumes of solids? That's fine. I'm just going to go over this then. Yeah, that's okay. I'll just help them in class, but you don't need this sister. Yeah, we're just going to go over some questions.
As I said, professor is here, 10 students are still here. This is disrespectful.
It's okay. I know sometimes they have to switch the system because they're using it somewhere else. So I'll go over the questions. It's okay.
Does it have any meaning in this country? No, I will repeat it again.
I'm just a worker.
I will repeat it for you, for your knowledge. Professor is still here. Do you know what that means?
Right. That's okay. We're just going to talk to the students and use it from here. So. Okay, so let's go ahead and pull this out. So this becomes when you square 81. So that's a constant with the pi. So it looks something like that. So 81 pi. Are you okay?
No.
Or what's wrong?
I really need to see.
Oh, is it just, oh, she just turned off the screen.
Yeah, we have no screen.
Oh.
So I'm trying to
Oh, that is kind of strange. I thought she at least had the screen on, but who knows? Maybe I'll ask her if she will put the screen on, because that doesn't affect. This is how we set it up. You got that set up so far?
I think I
Okay.
did that part right.
Yes. So 9 squared becomes 81, and I just pull that out front with the pi, because those are constants. So don't forget that part, because you got to square the volume. Yep. You can come and look on the right-hand shoulder if you want to look on this side. And then you'll have 1 over x squared plus 9 squared dx, right? Okay, so it has to be pi times the radius squared. 81 pi.
81 pi.
Don't forget the pi part. And then you have 1 over x squared plus 9 squared. Okay. So then, this is probably where you want to make a trig substitution, right? So this one, because you don't know how to integrate, this just as it is. So on this one, you'll just make x equals 3, let's see what would be it. This one tangent, right? This one you want to use a tangent for because it's x squared plus a constant.
I got that part.
Oh, good. So 3 tangent theta.
There are pieces I get.
And the derivative of 3 secant squared theta. D theta. Yeah?
That's what I got.
Okay. So, and then you could change your limits as well here. So like when x is 0, let's see what we get. When x is 0, tangent of theta would be 0, so theta is 0. And when tangent is, or x is 3, this will divide out and be 1, so the theta would have to be pi over 4. Does that make sense? Pi over 4. Because if you plug that in for 3, it divides out to 1. So where's the tangent equal to 1? Would be pi over 4. Okay, so then let's go ahead and plug everything in. So you still have the 81 pi out front, right? So 81 pi, new limit 0 to pi over 4. 1 over, this becomes 9 tangent squared theta plus 9 squared. And on the top, we'd have 3 secant squared theta, d theta, or 9, actually 9 secant squared. No, 3, sorry, that's just dx, so that is a 3. So 81 pi, 0 to pi over 4, are we at the right spot here? I'm replacing dx with 3 secant squared theta. And this becomes 9 tangent squared plus 9. So what this comes out here is a 9, right? And then tangent squared plus 1 is secant. So that becomes secant squared. But the 9 squared is 81, and that's going to cancel. So that will cancel the 81 out. But you will have a 3 pi. But then don't you just have, is it secant squared, they're gone?
This should be secant squared squared.
Secant squared squared. So secant to the 4th, so 1 over secant squared. I think you're right. So secant squared squared is secant to the 4th, so it'd be 1 over secant squared. And you have a 3 pi out front. How do you integrate 1 over secant squared?
It's an identity.
Yeah. Well, it becomes cosine squared. And then you could do power reducing. So let's see what we end up with. 1/2, what is that, 1 plus cosine of 2 theta. Yep. So now I have 3 pi over 2. Integrating that will be a theta plus 1/2. Yeah, so I got a theta. So I pulled up the 1/2, made it 3 pi over 2. And then I made it, the integral of 1 is theta, yep, plus 1/2 sine of 2 theta. And then plug in 0 to pi over 4. Yeah. So let's see. Plus, yeah, 1/2 sine of pi over 2, yeah. Plus 1/2. Minus, I think the rest of these, this will be 0. 0. Yep. Yep, so 3 pi over 8 plus 3 pi over, no, 3 pi squared over 8 plus 3 pi over 4. Well, because there was a pi times a pi I saw. Otherwise I was like, oh, those are the same, but they weren't. One has a squared. Ah. I think that's